Thank you. It's a pleasure to be here. As Pat just said, I'm going to be talking about this framework for characterizing gravity or dark energy on cosmological scales. Most of what I will be presenting is based on this paper that we submitted to Monras. And this work is done with my advisors, Roger Blanford and Bob Wagner, both at Stanford and part of the Kavli Institute there. Towards the end, I'll also present some results of constraints on the expansion history, and that work was done in part with Steve Allen and David Rapetti, also at Stanford. Right, so here's a brief synopsis of my talk. So when we started working on this project, the motivation was the following. If you look a few decades back, and we were in a position where we're not completely sure that GR was the right theory, a very nice framework was developed called the parametrized post-Newtonian framework to look from departures from GR, or to characterize GR better. And this has worked incredibly well and is still being used today. This framework was relevant for scales that were, for problems that had isolated sources. We wanted to go ahead and extend this framework, or try to develop a new framework that would serve the same purpose for cosmological scales. So that's what the overarching structure of the project was. But that's a big thing to do, at least for me at the moment. And for the purpose of this talk also, I wanted to focus on one aspect of this framework. The aspect that I'm going to concentrate on is a framework to sort of try to probe the relationship between the geometric part of gravity, that is the metric, okay, and the matter part, which is how's the matter distribution, and try to probe the relationship between the two. I'm going to restrict myself to linear subhorizon scales. So here's sort of motivation. As you all know, recent observations have told us that we have a pretty phenomenally successful model of our universe called the lambda CDM model. It's got a cosmological constant in it, which is causing the universe to accelerate, and weakly interacting particles, dark matter, which is responsible for the observed clumpiness of the universe. And this simple model has been confirmed, or at least is consistent with a large class of observations, such as standard ratios, that is the ratio of baryons to dark matter, in clusters with standard candles like supernovae, with CMB measurements, etc. And it's consistent within about a 10% at the moment. However, one should remember that dark matter has never been observed through non-gravitational means. We only know of it through gravitational means. And for lambda, I mean, it's up in the air. We don't know how to calculate its value. Okay. So phenomenologically, the model works, but there are still theoretical problems, big theoretical problems associated with it. This has led to a large number of theoretical alternatives being constructed, in particular to replace this lambda. Some of them include adding an additional field to your Einstein-Hilbert action with matter. This goes in the name of, for example, quintessence, or you could add something else, whatever you wanted there. If you're feeling more adventurous, you start modifying the Einstein-Hilbert action, and instead of the lambda, you start putting in arbitrary functions of the Ricci scalar. These models go in the name of f of r gravity. Or you could think about extra-dimensional models, such as this brain world model by Dvali, Gabadadze, and Parati, where gravity is truly 5-dimensional, but the matter is restricted to a brain, which is 4-dimensional. So many theoretical alternatives exist. In addition, because we have this 95% of the universe is unknown, a large number of observational efforts have been directed in trying to either constrain departures from lambda CDM or characterize it better. And these include missions like JDIM, SNAP, LSST, Planck, the Dark Energy Survey, etc. So given these observational and theoretical efforts that are underway, it would be nice to have a simple framework that for observers would provide a simple means of characterizing gravity, and it would streamline this approach with minimum amount of theoretical prejudice. On the other side, for theorists, it would give a nice way of comparing the observational consequences of different theories. It would provide them with a common language. So now, given the motivation, let's start thinking about how things can depart from lambda CDM. And the first thing that comes to mind is the expansion history can differ from what we expect from lambda CDM. For the first part of the talk, I'm just going to assume that this expansion history is constrained and known. I'll get back to this towards the end of the talk. But we have made kinematic measurements, and we know how the universe is expanding. I'll concentrate on the inhomogeneous universe, and this is where I think a lot of interesting stuff is happening. Talking about the inhomogeneous universe, the kind of questions you can start asking is, what is the growth rate of inhomogeneities? That is, if you have some matter distribution, how fast does it grow, or how slow does it grow? Does this differ from lambda CDM? You can go a bit deeper and start asking whether the relationship between the metric and the matter distribution is the same as it was in lambda CDM. And in particular, I was interested in asking whether there was a simple, more or less theory-independent way of characterizing this relationship and reducing the relationship to either a few functions or a few coefficients, which we could then go ahead and constrain. And if we are able to write down such a theory-independent relation, then you have to obviously ask what happens to all the additional fields that are present, the modification of field equations, how does this all enter into the system? So the question for most of the talk will be, how is the matter distribution related to the metric? Something that everybody is familiar with, a simple way of connecting the two, is the Poisson equation. Right? This is the equation we know and love. It's not really Newtonian gravity because we have subtracted out the background. But nevertheless, Laplacian of phi equals 4 pi g delta rho. Your delta is the fractional overdensity in matter. Rho is the non-relativistic matter density, the homogeneous part. Phi is the analog of the Newtonian potential. And g is, of course, the gravitational constant. It's easier to work in Fourier space, so you can transform it, and it looks like this. Your k is the co-moving wave vector, and h is the Hubble parameter. Now you start asking, how can you depart from this relationship? You assume this relationship is true on small scales, say 40 megaparsecs, and start asking, how can this relationship differ as you move to larger scales? Well, if you believe it's a relativistic theory, then the corrections will come in this form. They'll come in the form of gm over rc squared, which for Fourier space, or for the purposes of cosmology, in linear theory essentially corresponds to the size of the perturbation over size of the horizon squared. And that turns out to be this ah over k squared. This is all nice and good. So you start saying, OK, let me just start modifying this Poisson relationship and write down corrections to it that come in from a relativistic theory. And because you don't know what the coefficients are, I'll leave them arbitrary functions of time. Your scale factor is just used as a substitute for time. Now, you clearly see that there's a space in between. So initially, when we started working on this, we didn't expect anything to go in the middle. We just expected the first term to come in as ah over k squared. But then, after we worked through a little bit, we realized that we do need this extra term. And I'll get back to this when I discuss specific examples. Okay? So a linear term in ah over k can also appear, and I'll tell you why it can come in. Okay. Yes?
So one gauge, if you just change gauge a little bit, don't those also come in as part of h over k? I mean,
Not in this relationship. I mean, they come in a velocity relationship if you want. But how would you, what kind of gauge transformation? Yes, we have fixed Newtonian gauge here. Sorry, I should have said that. So we're working in Newtonian gauge for this purposes. We have fixed the gauge. Okay. So I've said, my claim is that this is more or less a generic relationship between the potential and the matter distribution, and that additional fields and everything can be incorporated into these coefficients. And I have to justify under what, this is not true in general, obviously. Okay, so what are the assumptions that go into it? And I'll discuss them in a little bit of detail. Of course, as you asked, I'm fixing to Newtonian gauge. There are two potentials and not just one, restricting myself to scalar perturbations. So for each potential phi and psi, I write down a relationship between phi and the matter distribution, and I put different coefficients in front of ah over k's. I also do the same for the matter over density. There's an additional part that comes in the form of initial conditions. That's this initial power spectrum that you have to put in. Just to orient people, this delta 0 that I've written in the third line is the usual growth function, or the growth function times a, depending on what you call it. Whereas g beta 0 can be thought of as the effective gravitational constant when you're talking about growth of structure.
So do you have an idea what kind of Lagrangian it corresponds to? It's high derivative terms.
No, these are not necessarily, you're just moving, these are not necessarily high derivative terms, right?
I think they are, because if you multiply things by higher powers of k, you have box
Well, if you could even if it's not a higher derivative, even if it's just k squared plus m squared, for example, that goes in there, if you Taylor expand in AH over k, it will give you this series. It doesn't have to be higher derivative theory to give you this. Right? So,
Do you have any idea what kind of, is there a Lagrangian form?
no, I haven't written down a Lagrangian form of this. So in the way we were thinking about this is that a higher derivative theory can also give you this, but even if you just Taylor expand the operators and move it to the other side, you will still get these power series. I mean, when I look at specific examples, you'll see what kind of Lagrangians can give rise to this expansion. So I don't have a general one, but I can tell you the series of models that we have considered, and they all fit this bill.
But the claim is it's most generic form you found.
Not the most generic. I mean, given, I'll take the assumptions, and you can question whether the assumptions are right or not. So it's not completely generic. I could have, for example, if I wrote down something that had a non-analytic operator, or something that was non-analytic in K, then this would not work. 1 over K, then this would clearly not work. So as you asked, what are the assumptions? Okay, I've assumed an expansion history. I've assumed a Poisson-like equation on small scales, and I'm expecting that my theory respects this fact. So this is an assumption I'm making. Then I'm saying that the corrections that come in as AH over K. Also, something that I've not talked in detail about is that I make this assumption that on small scales, the fluctuations in additional fields more or less follow or are proportional to fluctuations in the matter field. This is not true if you have dark energy, which has a very small sound speed, which essentially behaves like matter, because then you could have these additional terms coming in, and I can't do this. But for most quintessence models where you're expected to give cosmic acceleration, you will get that you don't get a very small sound speed. Okay? So this is it's not too bad of an assumption. And as I said, I've restricted myself to linear subhorizon perturbations. The range of scales that I'm talking about here is also limited because of the assumptions I've made. The yellow band essentially indicates the regions where this framework would be applicable. This lower limit, that is the smallest scales, are because I don't want to deal with nonlinearity, with all the astrophysics that's there. On large scales, it's simply because at cosmic variance are late times. Okay, so I have to box myself in because of that. You have to be careful because this AH over K is time dependent, so the physical reason is that it's small compared to the size of the horizon. That's what the physical parameter is.
That's strange. Potential usually is small even in the linear regime.
Right.
So the rho is increasing. The potential is always small.
Right.
Why do you need to restrict yourself?
Well, because then
This is about potential, not about direction.
because if I start including, I mean, for some of the models that you can consider, the Poisson equation no longer remains linear in delta. Sometimes you get delta squares coming in. So that's what I'm ignoring. Okay, so for FFR models, for example, if you just write Laplacian phi equals rho, sometimes there are higher terms in rho that come in. So that's something I'm ignoring here, so I can't do that. So you can, of course, towards the end, I will talk a little bit about how you can extend it to nonlinear scales. And you're exactly right. The delta rho, if that gets large, it's not terrible, because phi is still small, and we can just deal with phi completely. But let me get to that, hopefully, towards the end. So to make this sort of coefficient a little bit more concrete, let me just find out what they are in a bunch of models and tell you what they are. But this is not very difficult to do. And I'm going to discuss these models. They're essentially an increasing order of how the coefficients, what structure there is in the coefficients. Since I'm going to be doing calculations, I'm going to make some additional simplifying assumptions at the moment, which are not really necessary for the framework, but still helps in simplifying the calculations. I'm going to assume that on large scales, dark matter and baryons are essentially the same. There's, of course, some bias, but we'll assume that we understand this on large scales. Dark matter is covariantly conserved. You can do this more generally if you have the field equations where there's interaction. No problem with that, but I'm going to assume this for the calculations. The initial conditions are taken from the matter-dominated era rather than from the CMB, because I'm not including radiation at the moment. But you can extend this to do that, to include radiation as well. Just a reminder, the betas relate phi and delta, gammas relate psi and delta, and the delta coefficients are just related to delta. Now all I'm going to do is something that we're all familiar with doing. If you know that a differential equation has a power series solution, or a power law solution, you plug it in and you find what the coefficient, what the power is essentially the same thing here. You plug this into the field equation, you find out what the coefficients are. So if you plug it into the conservation equation, this is a conservation equation at first order in delta and phi. Q here is acceleration parameter, which is the opposite sign of the deceleration parameter that's usually used. If you start solving this equation in powers of AH over K, the first equation you get is this one right here. This is the usual growth of structure equation, except for the fact that this beta 0 coefficient describes your effective gravitational constant. Okay, so that could be, if that's different from 1, which comes about in many theories, then you would have an extra boost to the growth of structure or a suppression depending on how it comes in. If you go to next order in AH over K, you have a different equation, and you can solve order by order if you wanted. So here is the first example. Okay, this is the simplest example that one could think about. For an Einstein de Sitter universe, this universe just has matter in it and nothing else. And you calculate what the coefficients are. They're simple. They give you, all of them are constants. There are 1 for the first coefficient, 0 for the second one, and -3 for the third one. Okay. This is kind of nice. You make it a little bit more realistic, and you add a lambda to it, and you see that the first two coefficients still remain the same. And the third coefficient starts differing from -3 because of lambda. So this is where lambda is coming in this sort of an expansion. You want to make things a little bit more interesting, and you start dealing with quintessence, where you just put an additional scalar field, a slowly rolling one, and you see that there is a correction to, again, to only the third coefficient, and it comes in the form of the rolling of the scalar field. So this part does not differ too much from lambda CDN. Let me go into a bit more detail about why this fluctuation in the additional field are not really all that important. Well, here are the field equations for phi and the Einstein equation, including phi. If you write down the relationship between phi and delta matter, you'll find that there's an additional term, which is the ratio of delta phi over delta matter. But in the limit that AH over K is very small, you find that that ratio actually goes as AH over K to the 4th. So it's at higher order. So even if it's there, it doesn't contribute to this order. Make things a little bit more complicated. You start dealing with scalar tensor theories, where you've got this extra non-minimal coupling function coming in, and you see that the coefficient starts showing some differences. You start seeing that they split up. So far, all the coefficients have been equal to each other. They start splitting up. In the language of GR, this would correspond to anisotropic stress. So in the very early universe, when there were neutrinos, you also had the splitting up of coefficients. But that was because of anisotropic stress. In late time, if you don't have any significant contribution from neutrinos, then this could arise because of non-minimal coupling. So there's a split in the coefficients, but still, the second coefficient that I've written down is 0. The third one, again, splits up. I've written this down as power series in alpha, which is a coupling function, but you can write this down generally if you want. Let's go to another model, which is a brane world model. This is essentially a model where matter is restricted to a brane, gravity is 5-dimensional. The new scale entering into the problem is the ratio of the Planck masses in the two regimes, which is given by this RC. You calculate the coefficients, and again you find that the coefficients split up. This is an effective anisotropic stress. But the new thing that comes up in these models, which I alluded to in the beginning of the talk, is that the linear coefficient is non-zero. So let me try to say why this happens. So this linear coefficient is usually 0 because when you consider most theories, you'll have Laplacians, 4-dimensional theories, scalar field theories, you'll have Laplacians in them. If you move the operator to the other side, you'll get k² terms only. You won't get any k terms in this gauge. But when you start thinking of brane world models, you have an additional thing that you have to consider in the theory, which is the boundary condition between the brane and the bulk. There's a junction condition. If you think about this from the point of view of E&M, if you have a 2-dimensional charge sheet and your theory is actually 3-dimensional, when you relate the potential to the charge density, you actually get a gradient rather than a Laplacian. So there's a boundary condition. It's a jump across this boundary that gives you this AH over K term. So that's why it's appearing in the brain world models, and it doesn't appear elsewhere. So this, I think, would be an interesting thing to look for in cosmological observations. If you find this linear term, it is perhaps an indication of brain world models, which you wouldn't find in scalar field theories. Okay, for f of r gravity that people showed some interest in, here are what the coefficients look like. It behaves more or less like a scalar tensor theory in this regime. So you have an effective gravitational constant that's varying with time, and the coefficients, look a little bit ugly, but you can calculate them, and you see what they look like. Okay? They differ from lambda CDM in a scale-dependent way. So I've written down, so far I've told you that you can write down this relationship, and it's consistent with all of these theories that I've told you. So what it helps you do is it allows you to compare across models. Different coefficients tell you what kind of model, or different models will give you different coefficients. So if you go ahead and measure these things, it will tell you, at least in a gross way, which kind of model you're actually looking at. You can't get the linear term in models which have scalar fields and just GR, but you can get it in brain world models. So these are the kinds of things that come out of this. For observers, I think it would just be convenient to parameterize these coefficient functions in a simple way and try to measure them. So just a brief thing about observations. I'm not going to discuss them in detail, and I haven't done the analysis of how well you can do this, but I should at least tell you how, in principle, you can measure these coefficient functions. So for that purpose, you have to assume this basic thing that photons and baryons follow geodesics. If you don't do this, all hell breaks loose. Okay? You can't reinterpret observations easily. So I'm going to assume that. And as I said, I'm going to assume that baryons and dark matter are related in a simple way on large scales. The strategy would be the following. You want to compare the matter and the metric, right? So you want to measure both of these two things separately. How would you do this? There are two potentials, phi and psi. The combination phi plus psi enters into lensing, and it also enters into integrated Sachs-Wolf effect. So you can get that from those two observations. Whereas only one of the potentials enters into motion of non-relativistic matter, such as Hubble flows and so on, and that will give you the potential phi. On the other hand, the matter distribution you can measure with the help by just counting galaxies, counting clusters, and some correlation functions between them. So you can measure both of the two sides independently, construct, for example, power spectra, and look at how the relationship differs as compared to what you would expect from lambda CDM, and the difference is characterized by these coefficient functions. So as I said, so far I've talked completely about the inhomogeneous universe, assuming that the homogeneous universe was very well known. Let me go back to the homogeneous universe. So the coefficient functions you can get once you know the background. Okay? You can't do this. Otherwise, there would be degeneracy with the background that you couldn't get rid of. So you need to constrain the background first. So let me talk about how to do that. The simple question you ask is, how does the background expansion history differ from lambda CDM, and how can you characterize it? What I'm going to be talking about is sort of simple, and perhaps many of you might know this, but let me just go over it to set up what I'm going to say. So here is the lambda CDM expansion history. This is the scale factor. It grows as t to the 2/3 at early times. At late times, it goes e to the ht. Start taking the first derivative, and this is the Hubble parameter. It looks like this. Take the second derivative, appropriately characterized, and you see that there's a transition from deceleration to acceleration. If you're bored, you would go ahead and take the third derivative, and you find that this jerk parameter, which is essentially the next parameter in this series, that turns out to be 1 for all time in lambda CDM. So if the fact that this is 1 gives you a nice way of characterizing departures from lambda CDM. You're not going to go and measure jerk directly, but you can characterize your expansion history in terms of the jerk and try to measure it. Some useful things about this is that it is related simply to, if you relate it, so far it was kinematic, if you relate it to the total pressure of the universe, it's just a measure of the rate of change of the total pressure. It also characterizes the transition between deceleration and acceleration. And it's a good discriminator between some of the models. And this is very similar to the to state finder variables that were done before. And you can use the usual observations of kinematic observations to constrain the expansion history. We did this, and we found the following results. This is 2 years old, so it's not really up to date. We used clusters of galaxies where we assumed that more or less the ratio of baryons to dark matter is a constant. And we used the standard ratio to probe distances, essentially using it in a similar way as supernovae. And we also use supernovae, and combining the results, we see the following. So on this side, you see the usual W omega matter plot. On the other side, you see JQ naught. Q naught is the present deceleration parameter. You combine the results, and you see the following. No surprises here. It's consistent with lambda CDM. I mean, you see that it's sure the jerk is above 1. 1 is the line for lambda CDM, but it's consistent. I mean, this is the same thing that was found in W omega matter, that it prefers slightly more negative values of W, but it's consistent. So I wouldn't read more into this than the fact that 2 different sets of parameterizations, which have almost nothing to do with each other a priori, give you the same consistency with lambda CDM. So it's nice to see that. So you could use that to characterize the expansion history, but beyond that, there's not much you can do with that. So going back to what I started with, right? I started with saying that I wanted to construct something similar to the PPN framework, which was developed for solar system scales. I'm clearly not there. Okay? Why? Because the PPN case, it was really nice to have constants instead of coefficient functions of time. And I haven't reduced this down to simple coefficients, and that's what you would really like to do. But that, so far, I haven't come up with a simple way of doing that. There's also this problem that, I made the assumptions about what the energy momentum tensor should do, which you didn't really have to do in the PPN case. You had, for example, if you're dealing with the sun, you pretty much knew what the sun was doing. You knew that it was not a relativistic source. So you could do concrete things with that. In this case, you have to make some assumptions about this, and you would want to go beyond this and perhaps construct something more general. Also, there's a vast range of scales. I haven't talked about superhorizon and Londonian scales here, so you would want to include those as well. Hu and Savitsky, in a recent paper, tried to do this. What they did was they started with a Poisson-like equation on the scales, on small scales, and then they said that they use this relationship between the 2 metric potentials and superhorizon scales when you're in the limit that k goes to 0, and they tried to merge these 2 relationships by a fitting function. It's just a phenomenological fitting function, and that seems to work reasonably well with DGP and FFR models, but it remains to be seen where it works in general. Something that we differ on with what they have done and what the results we have is that they don't get the linear AH over K term for DGP models. So this is something we are looking into as to. It could just be that their fitting function, they've developed a fitting function, so it might just be missing that term. But we're looking into that to see why there's a difference.
Was the presence of that term gauge-independent statement, or was that?
In the Newtonian gauge, that term appears. I don't know what you mean by. So I haven't done the calculation.
If you did a general extension like this without fixing the gauge first, is it a generic statement that I would get a linear term in these constructions?
I think you would, because so you can write down the relationship between the potentials in Newtonian gauge, right? They're gauge invariant. So you can take that, and the matter part you can write this co-moving density perturbation, which is gauge invariant. Okay. It's a combination of the velocity part and this part, and then you would still. I think I did this when I started with this. You still get the linear term coming in. So I think it is a gauge independent, but I have to look into this more carefully. Because I think I could write them down in terms of gauge-independent variables, and you would still get an extra term, which was linear. But don't take my word for it at the moment. I should look at it more carefully. I haven't included tensor of vector perturbation, so this clearly needs to be done. I need to, if I want to convince any observers to use this, I need to provide simple parameterizations for the functions so that they can go and measure these. And there are many other related works that people have worked on, but the difference between most of them and the work that we have done is they don't look at scale-dependent departures. They're only looking at the Poissonic version and make the Newtonian constant time dependent. Okay? And they only look at the first term. That's perhaps because data at the moment it's hard to get the coefficients of the next terms because those are small. How much time do I have? Oh, I have a lot of time more. Okay, so I clearly went way too fast compared to what I was expecting to go through. Okay, so this was essentially the first part of the talk about relating the matter distribution to the metric perturbations. And I also gave you some constraints on how the expansion history can be constrained. Let me move on to something completely different, which has nothing to do with this talk, but since I have time, let me talk about this one project that I've worked on recently that I talked over lunch with people that I was out with. And this is about relativistic dark matter at the galactic center. A completely different topic. Nothing to do with what I said before. And this part is essentially about, you've got dark matter, you usually think it's not interacting, it doesn't do anything, but you get it dense enough and it starts annihilating. Look at the galactic center, it's a really dense region, you expect to see a flux from there. Most of the time when people do these calculations, they imagine that the flux or that the cross-section is independent of the velocity of the incoming particles, and that is significantly suppressed, and this is true in a lot of cases. But it's not true in general, and we try to explore what this velocity dependence would do. So we split the cross-section into two parts, the S-wave part and the P-wave part. In the class of models that we considered, you can see that the cross-section increases by orders of magnitude compared to simply the S-wave part as a function of V over C. And we tried to see how the flux would change as a function when we tried to incorporate this effect. And the flux can change for realistic models by a factor of 4 from the galactic center. You might think, well, this can't really happen because the region around the galactic center is so small, and V over C is only large in this small region, then how can this happen? The reason is that we assume that some sort of a density spike existed in the center. And because there's a rho squared dependence in the annihilation cross-section, that gives you a large contribution from the galactic center. And so you can increase your flux by a factor of 4, even up to an order of magnitude. This is an interesting result that came out of the simple calculation. We tried to do this with neutron stars as well, as to what would happen if you had a neutron star, going through our halo, capturing particles. Again, it's a relativistic environment. But what you get is not very promising, simply because if you're capturing things inside a neutron star, you're only going to capture about 10 to the 26 particles per year. A neutron star has 10 to the 57 particles sitting there. You're not going to do much to the neutron star with this. So it's not really a useful thing to consider unless it's happening outside the neutron star. Nothing else is going to happen. The first approximation, when we looked at the galactic center, you not only change the annihilation signal, you also change the profile towards the center because your annihilations become more efficient very close to the galactic center. So you sort of cap off the density towards the center. And that's what the plots on this side are meant to show, that you cap off the density. You can't go on increasing indefinitely towards the galactic center. On this side, you see plots of this core radius as a function of sigma v1 and sigma v0, which also depends on this. One of the things that's very difficult to know from astrophysics right now is the profile towards the center of the galaxy. And that is essentially characterized by this gamma spike, which tells you how steep your profile is. And all our answers sort of depend on this spike. We assumed a fiducial value of 3/2, but you have to, you have to somehow express your answers in terms of this gamma spike, and you can see that it varies quite significantly as a function of this gamma spike. So you have to take this with a grain of salt, that unless you know the profile, you can't really make strong predictions about what the annihilation signal will look like. Okay, I think that's pretty much what I had to say. So thank you. Let me go back to... So I don't have any constraints at the moment because I just haven't done the work on constraining them. But I think you would need, I know what you would essentially need. You would need the lensing power spectrum to be at the level of 1% to have realistic ideas, realistic ways of constraining these coefficient functions or departures from lambda CDM. On scales of 40 megaparsecs to 400 megaparsecs. So it's not, sorry?
They have the sheer power spectrum from
LSST or something, yeah.
You know what
Sorry?
you could look up what the error is.
No, you can look up what the errors is, but till there are two parts, right? There's the part about the LSST lensing power spectrum, and then there's the part about the matter. You need both of them to get the coefficients. And I just don't know exactly. I could look it up, and I could tell you that, okay, this is what they're claiming to be, and this is what kinds of constraints you've got. I just haven't done that correctly.
You mentioned in your first talk that one of your assumptions was that particles and light follow geodesics.
Uh-huh.
Is there any model existing in which particles and light do not follow geodesics?
I mean, you could couple it. You could couple it to a scalar, to another scalar field, where you're not. I mean, in this. So when I say follow geodesics, I'm assuming there is a physical metric of which these guys follow geodesics. You can always, of course, write down a metric for which these particles will follow geodesics. You could also. It could also happen that the particles and or baryons and light don't follow the same paths as dark matter would, because it's coupled differently than matter. So that's what I mean. So I'm assuming that if you have a single metric, the dark matter might not follow the same geodesics as your baryonic matter, because it's coupled to another field, and it feels that extra fifth force. So that's what I meant. It was not meant to say that you have no metric. There is a metric theory. So as long as you have a metric theory, they'll follow you. You'll get geodesics. Yes.
So like you were saying, when you were plugging into the conservation of mu,
Uh-huh.
the equation and various coefficients, like you were assuming that the stress energy is sort of characterized by the density perturbation. Do you have? Does it? So if you allow pressure and you allow anisotropic stress,
Uh-huh.
do you think that those things will introduce sort of exact degeneracies with respect to gravitational modifications, or like, for example, you were saying for these
You're right.
you get splitting between these parameters and that could be
Mhm.
by an anisotropic stress.
So.
Sort of thing where it's exact dynamics.
So the exact statement of degeneracy, it's a very good question, right? The exact statement of degeneracy is that I can take an FFR model, for example, a modified gravity model, and I can make it into a quintessence-like model, and I could get what that would do is give you coupling between the matter and the field. So if you want to just, the question you're asking is, can you always map modified gravity theory to something in GR with some weird energy momentum tensor? The answer to that question is yes, you can always do that, because I can always move something to the other side. But if you're going to restrict yourself to theories where the matter only couples minimally, then the mapping cannot be exact. Does that make sense? So if I write down Einstein's equations, right, and I split it in the part which is g mu nu, then some part which is either due to effect, say first it is due to a modification of gravity, equals t mu nu, which is the energy momentum tensor for, say, matter. I can always move it to the other side and call it some other energy momentum tensor. But that doesn't guarantee that that I can write down the stress energy tensor in such a way that it will not couple, that there will be no interaction between the two components. So right now I'm assuming matter is covariantly conserved. If you do the other ones, you can get interaction between the two components that you did not have before. So restricting the fact that you have no interaction and the fact that, so if you restrict yourself to having no interactions, then the mapping is not unique. But if you